Hello, I'm Nobutaka Shimizu of the University of Tokyo. I'd like to talk about quasi-majority functional voting and expander graphs. This is a joint work with Takeharu Shiraga of Chiyo University. I begin with introducing voting processes. In voting process, we consider a graph where each vertex has a binary opinion. We call this opinion assignment configuration. In a voting process, all vertices simultaneously update their opinion according to a predefined rule. And we repeat this synchronous update until all the vertices have the same opinion. These videos show examples. There are many applications of voting process. For example, voting process is known to be an effective approach to the consensus problem in the area of distributed computing. Now let me introduce three examples: pool voting, best of two, and best of three. In pool voting, at each round, each vertex picks up a neighbor uniformly at random. Then the vertex adopts a neighbor's opinion. In the figure, a green vertex picks up a red vertex, so this guy will let. In best of two, each vertex picks up two random neighbors with replacement. Then the vertex adopts a majority among the three opinions. The opinions of the two random neighbors and its own opinion. In the figure, a green vertex picks up red vertices twice, so this guy will let. In best of three, each vertex picks up three random neighbors with replacement. Then the vertex holds the majority among the opinions of the three. In the figure, a green vertex picks up two red vertices and one green vertex, so this guy will let in the next round. Note that if all vertices have the same opinion, this three voting process does not change its configuration, and this configuration is called consensus. This simulation shows best of two over complete graph. Our interest is the consensus time, that is the number of rounds to reach consensus. From this video, you observe that the best of two reaches consensus quickly. Here is our framework. Let AT be the set of red vertices at round T. A0 is the initial configuration. Then the consensus time T-const A is the heating time defined in the second item. Here, A represents the initial configuration. We say that the event holds with high probability if the event holds with probability at least 1 minus polynomial inverse. Here, n is the number of vertices of the underlying graph we consider. In this work, we assume that the underlying graph is connected and non-bipartite. Now, we present previous results. Pool voting has been well explored since the 50s in the literature of interactive particle systems. It is known that on any graph and any initial configuration, the expected consensus time is order n cubic. Moreover, on expander graphs, the expected consensus time is linear. Pool voting has a nice property called linearity, and this provides the rich theory of pool voting. Best of two is introduced recently. In the pioneering paper of Dura et al., they considered best of two on complete graphs. They proved that the consensus time is of the log n with a probability for any initial configuration. So best of two is much faster than pool voting on complete graphs. Also, there's a line of works that studies best of two on expander graphs. Roughly speaking, the consensus time is of the log n with a probability under the assumption of initial bias. There are several works that considered best of two on other type of graphs. But most of them also put the assumption on initial bias. Very recently, Shimizu and Shiraga proved that the consensus time is order log n on Erdős-Rényi random graph G and P if P is a constant. In their work, they did not put any assumption on initial bias. In summary, the worst-case analysis of consensus time with respect to initial configuration is difficult if the underlying graph is not complete graph. Best of 3 is introduced by Vecchietti et al. In 2014. Similar to best of 2, best of 3 reaches consensus within order log rounds with hyperability on a complete graph. And there is a work that studies best of 3 on expander graphs and dense graphs and Erdős-Rényi random graphs. But the consensus time of best of 3 is less understood compared to best of 2. An important thing is that best of 2, best of 3, and other bonding processes are studied via their own specific methods. In this work, we integrate the previous known results. First, we propose a general class of voting processes that contains best of 2 and best of 3 as special cases. Second, we prove that for the proposed voting process, the consensus time on expanded graphs is orthogonal with hyperability for any initial configuration. So this result extends previous works. Finally, we studied best of k. This is a natural generalization of best of 2 and best of 3, and we proved that the consensus time is order log n over log k on expanded graphs. We omit the detail of this result due to the time constraint. Now I propose the general class of voting processes. First, we begin with 4 basic notations. Let A be the set of vertices, set of red vertices, and B be the set of vertices with that is green. Let A prime be the set of red vertices in the beginning of the next round. So A prime is the random variable. Similarly, we define B prime. For vertex V, let NV be the set of neighbors of V. And for vertex subset S and vertex V, let digs V be the cardinality of the intersection of NV and S. So the degree of V is equal to the dig VV. Now we define functional voting. For function f, functional voting with respect to f is a voting process that satisfies the 2 conditions below. The first condition says that the probability that a green vertex V becomes red in the next round depends on the ratio of red neighbors. Similarly, the second condition is about the probability that the red vertex becomes green. So, in functional voting process, the opinion change probability can be written as a function of the ratio of neighbors that hold the opposite side opinion. We call this function f betrayal function. Also, we define a function hf here, and we call hf update function. And we will give an intuition behind hf later. Here are examples of function voting. Pool voting is a function voting with respect to x. And best of 2 is a function voting with respect to x squared. To see this, in best of 2, see the figure right. In this example, a green vertex will be red only if both of 2 random neighbors are red. So we have that the best of 2 is a function voting with respect to x squared. Best of 3 is a function voting with respect to 3x squared minus 2x cubic. In best of 3, a green vertex will be let if at least 2 of 3 random neighbors are let. So the opinion change probability can be written as a binary distribution. So we obtain this function. Now I give an intuition behind the update function HF briefly. Let alpha be the ratio of A and alpha prime be that of A prime. If we fix A, then alpha prime can be written as the sum of independent random variables. So alpha prime is concentrated on its mean. Indeed, on a complete graph, we can easily compute the mean of alpha prime. And actually, this is equal to HF of alpha. So due to the concentration of alpha prime, the behavior of alpha can be roughly expressed as the iteration of applying HF. So HF plays a key role in the study of functional voting process on a complete graph. Now we introduce a subclass of functional voting process. Functional voting with respect to f is quasi-majority if it satisfies the 5 conditions below. First, the function f is smooth. And second, f of 1/2 lies between 0 and 1. These two conditions are due to technical reasons, and they are not so important here. The third condition requires that hfx is less than x in the right half area. The fourth and fifth conditions are about the slope of hf. We note that the function hf has a point symmetry at the point 1/2, 1/2, as shown in the figure. So the third condition implies that hfx is larger than x, where all x between 1/2 and 1. Best of 2 and best of 3 are quasi-majority, but pure voting is not. Here, we define our target graphs. A graph is lambda expander if the absolute non-trivial eigenvalue of the transition matrix is at most lambda. Here, we consider the transition matrix of the simple random walk. For example, it is known that an Erdős-Rényi graph GNP is order 1 over square root of NP expanded with hyperability. Also, we consider mildly regular graph. Consider the stationary distribution pi of the simple random walk. This is a vector. A graph is mildly regular if the 2 norm and 3 norm of pi are small, like this. Roughly speaking, the norm of pi measures the balance of the degree sequence. So a regular graph has a small norm, but a star graph has a large norm. Now we give our main result. Consider a quasi-majority function voting over order n to the minus 1 over 4 expanded and mildly regular graph. Then the consensus time is at most order log n with hyperability for any initial configuration A. Moreover, this upper bound is tight up to a constant factor. This main result is the worst case consensus time of the quasi-majority function voting on expander graphs. In the second result, we obtain a similar bounds of consensus time on sparse expander graphs. But here, we put an initial bias assumption. These two results generalize and extend previous works of best of 2 and best of 3 on expander graphs. Here are corollaries directly follow from our main result. The first one considers best of 2 and best of 3 on Erdős-Rényi graphs. The result says that the consensus time meets all log-n with hyperability for initial configuration, and this improves previous work. The second one considers random regular graphs, and our result says that if the degree is larger than square root of n, then we can obtain the similar bounds. Actually, there is a previous work that studies best of 2 on random regular graph, and the result put an assumption on initial bias. But in our result, we consider dense random regular graph, but we could remove the initial bias assumption. Quasi-majority functional voting contains wide range of voting processes other than best of 2 and best of 3. For example, we can consider Takeharu voting like this. In Takeharu voting, a vertex V picks up k random neighbors. If all of the neighbors hold the same opinion, V adopts it. Otherwise, the vertex V keeps its own opinion. We can easily see that this is a quasi-majority function voting with respect to x to the k. Another example is the lazy variant of voting processes. For example, in low lazy best of 2, a vertex V tosses a private coin with head probability low. And if the coin is head, then the vertex V performs best of 2. Otherwise, V does nothing. We can easily see that low lazy best of 2 is quasi-majority if rho is a constant. So, quasi-majority function voting contains several natural voting processes, and we can obtain bounds of the consensus time from our main result. This is our strength of our result. The rest of this talk is devoted to present proof of line of the main result. Best of 2 and best of 3 on complete graphs have been already studied, and we use their technique. In general, a voting process is a Markov chain or a family of vertex subsets. But on complete graph, the state space of the chain has size n plus 1. So our perspective is that this holds even for expander graphs. Consider a function voting over a complete graph Kn. Let alpha be the ratio of A and alpha prime be that of A prime. So alpha prime can be written as independent random variables. So from the chain of bound, we can say that the alpha prime is equal to hf of alpha plus minus some small term with hyperability. If the initial point alpha is away from 1/2, then the orbit of alpha can be roughly approximated by the duration of hf, as shown in this figure. Therefore, from the properties of hf, we can obtain an upper bound of the consensus time. The difficult case is that the initial alpha is close to the middle point. To deal with this case, we use the useful result from the previous work. Here is the informal statement of the result. Roughly speaking, the result says that alpha escapes from the middle point within order log n rounds if both of the following two conditions hold. The first condition requires that alpha prime has a fluctuation of size 1 over square root of n with constant probability. The second condition essentially requires the drift towards outside of the middle area. it is easy to see that the second condition holds from the property of HF. And the technical part is to verify the first condition. To this end, we use the central limit theorem. This theorem says that alpha prime has a fluctuation of size square root of variance of alpha prime with constant probability. So we need to estimate the variance of alpha prime. On complete graphs, we can easily evaluate this variance, and we are done. In this work, we consider expander graphs, and our technical ingredient is to evaluate the expectation and variant of alpha prime on expander graphs. Roughly speaking, the expectation and variance of the alpha prime on expander graphs are the same as that on complete graphs. In the expectation, the additive gap is order lambda square. And if this gap is less than 1 over square root of n, then we can apply the result in the previous slide, this result. The core of the proof of the estimation is a variant of the expander mixing lemma. Indeed, to the best of our knowledge, previous works about the best of 2 on the expander graphs did not evaluate the variance of alpha prime. And this is the reason for the lack of worst-case consensus time analysis. Here is the conclusion. We propose a general voting process that contains best of 2 and best of 3 as special cases. And we obtain the worst-case consensus time of this model on expander graphs. The proof uses several previous techniques. But the core, our technical ingredient, is the evaluation of the expectation and the variant of alpha prime. This is the end of this talk. Thanks for joining this talk.